Hello everyone, this is Jimmy. In this lesson, I will talk about the architecture of smart contracts in the Neo blockchain. I will explain what are the conditions of a smart contract, its context, API, as well as an example of a complex smart contract. Architecture features. In one of the previous lessons, we have discussed the positive aspects of the smart contract created on the Neo blockchain. Accuracy. One such positive aspect was the high accuracy of the contract. This accuracy is ensured by the fact that the blockchain is a system that works on the basis of many nodes. These nodes are computers, as we discussed before, including several times on the same node. In this case, the program behavior should be predictable. That is, the same input data should always produce the same result. Blockchain is a multi-user storage and computational method where the data in the distributed system are the result of reliable calculations that cannot be tampered with. Smart contracts work in this multi-node distributed network. If the smart contract is a non-deterministic, the results of different nodes may be inconsistent. As a result, consensus between the nodes cannot be reached or even completely disappear into a fork. Therefore, when developing a system of a smart contract, it's necessary to exclude any factors that may lead to a non-deterministic behavior. Work with time values. Retrieving system time is a very common system function that can be widely used in certain time-dependent contract procedures. However, obtaining system time is a non-deterministic system function, and it's difficult to obtain a single accurate time in a distributed system since the results of different nodes will be contradictory. NeoContract provides a block-based system that processes the entire blockchain as a timestamp server and receives a timestamp when a new block is created. On average, the Neo network generates a new block every 15 seconds. So the contract is executed at about the same time as the last block, plus or minus 15 seconds. Randomness. Many smart contracts, such as gambling and small games, use random number functions. However, random number functions are a typical non-deterministic function, and each system call will receive different results. In a distributed system, there are many ways to solve this issue. First, the same random initial number can be used for all nodes, so that the reverse sequence of the entire random function is deterministic. But this method provides the entire random result in advance, significantly reducing the practical value of the random number. Another possible solution is for all nodes to interact with each other to generate random numbers. This can be achieved by using cryptographic methods to obtain a fair random number. But the disadvantage is the very low performance and the need for additional communication overhead. A centralized random number provider can be used to generate random numbers, which ensures consistency and performance. But the disadvantage of this approach is obvious. Users will have to unconditionally trust the centralized number provider. There are two ways to generate a random number in Neo. First one, when each block is generated, the consensus node will reach a consensus on a random number and fill it in the nonce field of the new block. A contract program can easily get a random number from any block by referring to the nonce field. The second way, the contract program may use the block hash value as a random number generator, since the block hash value has certain randomness inherent in it. This method can be used to obtain a weak random number. Data sources. If a program receives data at runtime, it can become non-deterministic if the data source provides non-deterministic data. For example, using different search engines to get the top 10 search results for a particular keyword can give different results in different sort orders if different IP addresses are used. For smart contracts, Neo provides two types of deterministic data sources. The first one, blockchain ledger. The contract procedure can access all the data in the entire chain through interacting services. including complete blocks and transactions and each of their fields. The data in the blocks is deterministic and consistent, so they can be accessed safely using smart contracts. The second type, the reserved data storage location in the contract. Each contract deployed on the Neo network has a private storage area that only the contract can access. The Neo consistency mechanism ensures consistency in the storage state of each node in the network. In situations where access to non-blockchain data is required, Neo does not provide a direct way to interact with this data. Neo blockchain data must be transferred to the Neo blockchain using transactions, then transferred to any of the above data sources in order to become available for a smart contract. Smart contracts in Neo can call each other but not recursively. It can be achieved as part of the contract, but it cannot cross the boundaries of the current contract. In addition, the calling relationship between contracts must be static. The goal cannot be specified at runtime. This allows you to fully determine the behavior of the program before execution and to fully determine its relation to the call before its launch. Based on this, several contracts can be dynamically divided to achieve parallel execution. Smart contract execution and performance. Execution environment of a smart contract plays a very important role in its execution. When we analyze the performance of any runtime environment, there are two main indicators: speed of execution of instructions, the startup speed of the runtime itself. For smart contracts, the runtime is often more important than the speed at which instructions are executed. Smart contracts are more involved in the logic input-output to identify instructions where the implementation of these instructions can be easily optimized. Each time a smart contract is invoked, it must start a new virtual machine or container. Therefore, the execution speed of the environment itself, starting a virtual machine or container, has a great impact on the performance of the smart contract system. Neo uses the lightweight Neo VM, Neo Virtual Machine, as an intelligent contract execution environment that has a very fast startup and very few resources, which is ideal for short programs such as smart contracts. Using compilation and caching of smart contracts with a hotspot using JIT, just-in-time compiler, can significantly increase the efficiency of virtual machines. When discussing system scalability, two main areas are addressed: vertical scaling and horizontal scaling. Vertical scaling refers to the optimization of the processing workflow, which allows the system to fully utilize the capabilities of existing equipment. With this approach, system boundaries are easily achievable. Since series-based processing performance is based on the hardware limitation of a single device, when we need to scale a system, is there a way to turn a serial system into a parallel system? Theoretically, we will only need to increase the number of devices, and we can achieve almost unlimited scalability. Can we achieve unlimited scaling in networks with a distributed blockchain? In other words, can blockchain execute programs in parallel? The blockchain is a distributed register in which various states, data, and rules governing changes in the state of this data are recorded. Smart contracts are used as carriers to record these rules. Blockchains can process programs in parallel only if several smart contracts can be executed simultaneously in an inconsistent manner. In fact, if the contracts do not interact with each other or the contract does not change the same state data at the same time, their execution is not sequential and can be performed simultaneously. Otherwise, it can only be performed sequentially in sequential order, and the network cannot scale horizontally. Based on what we said, we can easily design unlimited scaling in smart contract systems. All we have to do is to set simple rules. A A smart contract can only change a state record that belongs to it. In the same batch of transactions block, the contract can be launched only once. As a result, all smart contracts can be processed in parallel, since the sequential order is not related to the result. However, if a smart contract can only change the status record of the contract to which it belongs, this means that the contracts cannot call one another. Each contract is an isolated environment. If in the same transaction lot block, the contract can be launched only once. This means that an asset issued with a smart contract can only process one transaction per block. This is a big difference with the initial goals of developing smart contracts, which are no longer smart. In the end, NEO design goals include both a reciprocal call between contracts and multiple calls to the same call in the same block. Fortunately, smart contracts in NEO have a static call relationship, and the purpose of the call cannot be specified at runtime. This allows you to fully determine the behavior of the program before execution and to fully determine its relation to the call before its launch. Each contract is required to explicitly indicate the contracts that can be invoked, so that the operating environment can calculate the complete call tree before executing the environment procedures and split the execution of the contracts based on the call tree. Contracts that can change the same state record are executed sequentially in the same section, as a result of which various sections can be executed in parallel. Low-level relationship creation. A relationship is a measure of dependence between two or more objects. The NEO contracting system uses a low-level communication construct that runs in NEO VM and communicates with non-block circuits through an interoperable level of interoperability. Smart contract runtime, context and API. Smart contract modes, verification contract. Unlike the public key account system used in Bitcoins, the NEO account system uses a contract account system. Each NEO account corresponds to a verification contract, and the hash value of the verification agreement is the address of the account. The software logic of the verification agreement controls account ownership. When transferring from an account, you must first draw up a verification agreement for this account. The verification contract can take a set of parameters, usually a digital signature or other criteria, and return a logical value after the verification. The verification contract can take a set of parameters, usually a digital signature or other criteria, and return a logical value after the verification, indicating the success of verification in the system. The user can pre-deploy the verification contract on the blockchain or publish the contents of the contract directly in the transaction during the transfer process. Application contract. The application contract is initiated by a special transaction that can access and change the global state of the system, as well as the private state of the contract storage area at runtime. For example, you can create a global digital asset in a contract, vote, save data, and even dynamically create a new contract when the contract is executed. Executing an application smart contract requires resources for executing instructions. Without a transaction, the contract stops the execution, and all state changes will return to the previous state. However, the validity of the transaction does not depend on whether the contract has received success or revert status. A function contract is used to provide some publicly or frequently used functions that may be called by other contracts. The smart contract code can be reused, so developers can write more and more complex business logic. Each contract for a function during deployment can choose a private storage area, which will either be read or written to data in a future contract, ensuring a constant state. The contract of the function must be previously deployed in the chain that will be called and removed from the chain of the self-destructive system function, which will no longer be used, and its personal storage will be destroyed. The data of the old contract can be automatically transferred to another subcontract until it's destroyed using the contract migration tools. Using function contracts, you can pretty easily organize an API point system for some other contracts. Virtual machine. NeoVM provides a virtual layer of executing smart contracts. Its main parts are central processing unit, the call stack, the stack of calculations, temporary stack. CPU. It's responsible for reading and sequentially organizes the execution of instructions in the contract according to the function of controlling the flow of commands, arithmetic operations, logical operations. The future of the CPU function can be expanded by introducing the JIT function, real-time compiler, call environment, used to store contextual information about the execution of the program each time the function is called, so that it can continue to be executed in the current context after the function completes execution and return. Computing state. All NeoVM runtime data is stored in the computing stack. When after executing various instructions, the stack will be calculated using the corresponding data elements of the operation. For example, when additional instructions are executed, the two operations involved in the addition are retrieved from the calculation stack, and the addition result is transferred to the top of the stack. Function call parameters must also be calculated from the right to left in accordance with the stack order. After the function succeeds, the top of the stack fetch function returns a value. Temporary stack. When you need to schedule or rearrange items on a stack, you can temporarily save the items on a spare stack and retrieve them in the future. Instruction set. NeoVM provides a set of simple and practical instructions for building smart contract programs. By function, the main categories are as follows: constants instructions, process control instructions, stack operating instructions, string instructions, logical instruction, arithmetic instructions. We also have cryptographic instructions and data instructions. It's worth nothing that the NeoVM instruction set provides a series of cryptographic instructions, such as ECDSA, SHA, and other algorithms to optimize the effectiveness of the implementation of cryptographic algorithms in smart contracts. In addition, data processing instructions directly support arrays and complex data structures. Interoperable service layer. The virtual machine on which the smart contract is executed is a sandbox environment, which requires a multi-threaded service level when access to data outside the sandbox or data persistence at runtime is required. At this service level, a Neo contract can use a series of system functions and services through its internal operations, and such a contract can be called up and accessed to internal functions in the same way as normal functions. All system functions are performed simultaneously, so there is no need to worry about scalability. Blockchain register. A smart contract can receive complete block data from the blockchain, including all information about the block or transactions and each of their fields. At runtime, using the system functions provided by the multi-threaded service level, in particular, you can request the following data: blockchain height, block title, the current block, transactions, the type of transaction, its attributes, input and output data of the transaction, and much more. Using this data, you can develop various interesting applications such as automatic payments or smart contracts based on proof of work. Expenses. Deployment fee. The distributed Neo architecture provides high redundancy in storage capacity, and the use of this capacity is not free. The deployment of an intelligent contract on a Neo network requires a fee, which currently ranges between 100 and 1000 gas, depending on the capabilities required by the contract. This fee is charged by the system and it's recorded as a system gain. Future fees will be adjusted according to the actual operating costs in the system. A smart contract deployed on the blockchain can be used several times until it's destroyed by the developer. Fulfillment fee. Neo provides a reliable runtime for smart contracts and a contract execution requires computational resources for each node, so users must pay for smart contracts. The fee is determined by the computing resources consumed at each execution, and the unit price is also indicated in gas. If the implementation of a smart contract failed due to the lack of gas, the cost of consumption will not be returned, and this will prevent malicious attacks on the power consumption of the network. For most simple contracts, they can be executed for free if the execution costs remains below 10 gas, which significantly reduces the cost for the user. Crowd sale contract development. In one of the previous lessons, we demonstrated the creation of the NEP5 contract token. Now I would like to show a more complex crowd sale contract. Typically, token contracts are part of a crowd sale contract. We are currently looking at the Nash community contract crowd sale template. Nash is a blockchain-based neo exchange. Let's open the crowd sale contract. As we can see, at the top of the contract, imports from the NeoBoa library are displayed, as well as additional functions located in other directories of this application. We see that in the contract there are 3 events responsible for the functions of the contract. Let's look at the KYC function. This function is responsible for verifying users. Most often, it's used in crowd sale contracts so that the user who has not passed verification cannot buy tokens by sending funds to the address of the crowd sale contract. KYC register, as we can see, can only be called by the owner of the contract and writes the user address in the storage space of the contract. KYC status function. This function makes it easy to determine if you are a verified user through KYC or not. The function is quite simple. First, the argument is checked. It's necessary to pass a specific address, which allows the contract to check whether this address is contained in its state. If the address is contained in this contract, the contract returns the status. Next, we have the perform exchange function. This function is necessary to exchange investments for tokens. A special attachments function checks the amount of funds received. The next function is verification, called exchange OK. This function determines whether the exchange can be carried out further. Current balance. Calculate the current balance of the contract. Exchange tokens. Calculates the number of tokens for distribution. New total. Calculates the new amount of tokens that will be written to storage space. Result. Adds the received amount to the total number of tokens. Then there is an on-transfer event confirming that the transfer of tokens has been completed. Let's take a closer look at the can exchange function. This function checks whether the investor can exchange NEO or gas for his tokens. First, a check is made to see if any number of NEO or gas is attached. If not attached, then the check returns false. Then comes the KYC check. If the user is not in the contract list, then the check returns false. After a successful KYC check, the calculation is performed using the amount requested. The amount that the user attached is multiplied by the token rate. Next, an exchange OK check is carried out, which confirms whether the exchange can continue. The get KYC status function looks at the address status in the contract, makes a key, adds the values, and checks using the received key. The calculate can exchange function calculates the number of tokens that the investor will receive as bonuses. This function is very common in crowd sale contracts if stages are proposed and in which the bonus program is included. Let's determine block height. It's necessary to see how many tokens are on the contract, and the value of tokens that we took from the user is added and we get the total value. If this value is higher than total supply, then the transaction will be failed. If the total supply is not exceeded, the contract checks the current block in the blockchain to determine that the time for the sale of tokens has begun. Then there is a check whether the current round is completed or not, depending on the number of tokens planned for sale within this round. The contract also checks if the number of directed investments exceeds the offer of the current round. Then the transaction will fail. This contract provides specialized logic that checks whether the user has already bought tokens in the current round. With this, we completed the review of the crowd sale contract code and can familiarize ourselves with the contract token code. The code of the contract token should not differ much from the one we wrote in the previous practical lesson. The codes are almost identical. They differ only in names. At the beginning, we see imports, then a list of events, on transfer, on approve, introduced the head function and switch, operation and all standard function of NEP5. Let's take a look what additional features have been added to work with the crowd sale contract. An XTEXIO model has been added. It contains the getAssetAttachments function. This function takes information about the token that we attach to the transaction. It takes from an execution engine, getScript container. It takes transactions and look at the traces where the transaction appeared. Takes the recipient address, persists the values of NEO and gas. If the transaction was found, then we take a trace of this transaction, write down the script hash of the one who sent it. And through the transaction output field, for each output we check script hash, whether it's the same as the recipient address. Then check the asset ID. If asset ID is NEO, then we add the value NEO. If not, then it's gas and the value gas is added. After that, the full set of values, receiver address, sender address, sent amount NEO, sent amount gas is sent. Next, let's see what is located in the token file. The settings are collected in this file, this template. In our previous lesson, we wrote the contract from the beginning, while in this file it's compiled into a template for the convenience of creating the desired contract. Also in this template presents the settings of crowd sale, token initial amount, token per NEO, token per gas, max exchange limited round, KYC, etc. The limited round key field will display the number of participants in a limited round. The crowd sale available amount function returns the number of unsold tokens remaining on the crowd sale contract. This is what the crowd sale contract at NEO looks like. It looks similar in other blockchains, but the advantage of NEO is precisely in the possibility of using other high-level languages, in our case Python. This is where we end. In this lesson, we examined the architecture of NEO and smart contracts, studied the execution environment of smart contracts and the implementation of complex smart contract using the crowd sale contract as an example. Thank you for your attention and see you in the next lesson.